So we were proving quantum Bochner's theorem. Let me recall it. So the theorem, quantum Bochner's theorem. So let's recall it. F is some function from Cn to C, satisfying the following condition: f of 0 equal to 1. And we further have this f of alpha, sorry, k of alpha beta, k of alpha beta equal to e power iu, I mean, it was plus, no, plus imaginary part of alpha beta, f of beta minus alpha. Okay. This is positive definite. F of 0 is 1 and f is continuous. Okay. It's a continuous function from Cn. And so this is positive definite. So I forgot to say. F is a characteristic function of a function f from Cn to C is a characteristic function, is a function of a state on our H, our L2 of Rn or gamma of Cn, if and only if f satisfies this condition. F of 0 equal to 1, f is continuous, and this function, this is minus, this function is positive definite. Okay, this is the, so we have proved only if part. If it is a characteristic function, then we have, then this, it satisfies this is we have proved. So only if is proved. So we have to prove this direction. So if it's something satisfies this condition, then we have to prove that. We have to prove that it is a, we have to get a state on that. Okay. So this function, this k alpha beta equal to e power I imaginary part of alpha beta f of beta minus alpha. This is positive definite. Okay. So GNS or Kolmogorov construction or whatever implies the following. GNS implies there exists a Hilbert space. Let's call it K. There exists a Hilbert space K and a function lambda from the Cn to K, alpha going to lambda alpha going to lambda alpha, such that the following conditions are satisfied. Lambda alpha in Cn, it's total. Okay, it's total. That is span closure equal to K. This is what is called totality condition. Okay. And further, lambda alpha, this inner product, lambda alpha, lambda beta, is evaluated by the K function, which is actually I imaginary part of alpha beta, f of beta minus alpha. So last time we did the calculation, I think it is e power I plus imaginary part of alpha beta, f of beta minus alpha. Okay. So I think this is correct. So we have got this Hilbert space. On this Hilbert space, let us try to get the Weyl representation somehow. Okay, we get the, so this is the idea. We have got we have a positive definite function. Using that, we got a Hilbert space using GNS construction. On this, we do try to get a Weyl representation of it. Then we use Stone-von theorem to bring it to the Fock space, and we get a K. And using that, we try to get a state. So you will have the we evaluate the vacuum state on this Hilbert space. Whatever the vacuum state means, vacuum state will correspond to lambda of 0. Okay, it's always okay. So we use that vacuum state in this Hilbert space K to get the corresponding state. For that, we need some more things. So I've already used the lemma. I mean, which was in the Ghana 1 exam. the trace convergence, we will use that. And also we will use another thing which is called partial trace. You can tracing out something. Okay, that is also a question in your HSQP, but I don't think anybody did that. I was surprised. Okay, so that's also we will use. Okay, so that will be an assignment. I will give you the idea how that is proved. Okay. Okay, so we got the Hilbert space. Now you define U alpha. So we have to define it on the total set. We want to define a unitary. We define it on the total set. U alpha acting on lambda beta equal to. So since I have I there, it should be minus I. Anyway, we'll do the calculation. It will be clear. E power minus alpha beta lambda of alpha plus beta. So beta plus alpha. It's just the translation. Again, the same translation. Okay. So then what? So we want to see that this satisfies. So then first we want to see that this is a unitary. Okay. So U alpha lambda beta prime. First we want to check it's a unitary. Then we want to check it satisfies the Weyl commutation relation. Okay. Then we will use a Stone Von theorem. So claim number one. Claim U alpha is unitary. Okay. Well, this is the first claim. So we have to check the inner product. So U alpha lambda beta. So which is equal to, so the first one is conjugate linear, no? So e power minus, I take it out. So we get I imaginary part of I alpha beta. I mean, I do the calculation. So I swallow a few steps. Okay. We get a scalar in the first entry in the inner product. I take it out. Okay. As a conjugate. And the second entry will get something that also, that I take. I imaginary part of alpha beta. Okay. And this is linear, so minus I imaginary part of alpha beta prime. Okay, this is prime is clear, prime. Then the inner product of lambda beta plus alpha lambda beta prime plus alpha, right? So this is equal to, let's write the whole exponential inside the e power I imaginary part of alpha beta minus I imaginary part of alpha beta prime. Okay, the inner product between this is, that is given by the k function. So that is plus I times imaginary part of beta plus alpha beta prime plus alpha, right? Beta prime plus alpha. Then f of beta prime minus beta.
No, like f of.
Yeah. So then the whole thing, then f of. So yeah, it is just the alpha will cancel. So it is just beta prime minus beta. Correct. Okay. So, so few things should cancel. So I times imaginary part of alpha beta is here. So which is here?
Alpha beta prime.
Alpha beta, no, whether the sign is same. Alpha beta size here it's there. There is a beta here, there is an alpha here. Okay, and alpha beta, and the imaginary part of the conjugate of the inner product will be minus of that, right? So that will get cancelled. Okay, so this alpha beta, I mean, I don't want to write, let me write the final product. Okay, alpha beta, that will get cancelled, and alpha beta prime is there, that will also go away. So there are 4 terms in this. Alpha will be 0, right? So what is the remaining one? Beta prime, right? So imaginary part of I beta prime. So this is exponential I imaginary part of beta prime, and then f of beta prime minus beta, which is precisely the definition. It is just inner product of lambda beta and lambda beta prime. So this is unitary. Hence the claim, right? right? Hence the claim. So I just did the calculation, nothing else. You can do the calculation on your own. Just from the definition, we do the calculation and we get it. So these things imply, so U alpha preserves a unitary. No, this is just a total set. This lambda alpha is just a total set. Okay. And so this is the theorem which we proved last semester. So if you have a map, any map, you need not even worry about well-definedness or something. You need not even worry about well-definedness. You have some map which preserves the inner product on a total set, then you can extend it uniquely to the whole big set as a unitary, as a isometry. But if the range is also total, okay, the range is also total, that's also total, right? It's just the scalar times beta plus alpha. You can see that is also total. That beta plus alpha, once you fix an alpha, that is also total. It is just a translation, no? Beta varies over a whole Rn. Okay, it will be again Rn. So the range is also total. Scalar times some total set. So the range is also total. So it's a unitary. Okay. So hence the claim. U alpha extends to a unitary. It's not U alpha is not a unitary. U alpha extends to a unitary. Okay. We defined U alpha on a total set and it preserves the inner product on the total set. So we can extend linearly to the span and then to the closure. Okay, by the lemma we proved last semester. Okay. This is a basic trick. So you have got a unitary. Now we want to check for different alpha and alpha prime what happens. Okay. So let us check. So the next claim is U alpha in Rn satisfies the canonical commutation relation. Satisfies CCR. Okay. We call it CCR, canonical commutation relation. So what do you have to verify? You have to verify U alpha prime. Okay. So you have to verify how it acts on some lambda beta. Okay. Lambda beta. So it's clear. It's clear. U alpha. I should give this an assignment, but it's okay. We'll just do it. Okay. U alpha, which is just imaginary part of e power I imaginary part of beta alpha prime beta. Okay. Huh? Here it's negative. No, here it's positive. No, lambda definition is negative, right? Okay. Yeah, correct. Lambda definition is okay. Lambda beta plus alpha prime. Okay. Now again U alpha. So E of I imaginary part of alpha beta plus alpha prime. Okay. Minus I imaginary part of alpha prime beta. Okay. This translation is okay. This is just alpha prime plus alpha. Okay. Now here what happens? Here you have alpha. So you have imaginary part of I, imaginary part of alpha prime you have. Okay. And then this is just, you have just beta here. I mean, this is just alpha plus alpha prime beta, right? Right, that's all. Lambda of beta plus alpha prime. So which is precisely U of alpha plus alpha prime acting on lambda beta. Sorry, there's the scalar. This e power I imaginary part of alpha prime times this. Okay, hence the claim. We just use the definition. It satisfies this condition on a total set. So it should satisfy. This condition is a linear condition. Okay. So if it is enough to verify, it satisfies on. I mean, these arguments are there. I mean, we used to it. So I just direct. Actually, we are verifying this condition on a total set. If it satisfies on a total set, it is satisfied for the operator. Okay. So it's hence a claim. So now Stone-Von Neumann theorem. von Neumann theorem implies there exists a small Hilbert space. So there exists a Hilbert space K and something, but you can assume that itself, I mean, so using Stone von Neumann theorem, we can assume that this K is equal to that. There exists a U from something, and we assume that. So by Stone von Neumann theorem, because we want to prove the whole thing up to unitary, we want to get a state up to unitary. Okay, so yeah, I mean, otherwise you use the unitary to get the state. I mean, if you have a state on here, another Hilbert space, if you have a unitary, you can take this state to by U star, you can use that to get a state on the another Hilbert space, right? If you have a state on one Hilbert space, you have a unitary to another Hilbert space, then using this unitary, you can get a state on the another Hilbert space. You can conjugate U star. If you just use that, you will get a state on the another Hilbert space. Okay. So we can assume that the unitary is not there. We can assume that. So we can assume without loss of generality. Otherwise, you have to use that U somewhere. Okay. We can assume without loss of generality that our K is nothing but L2 of R tensor K, small k, for some K. Space K. Okay. And U alpha equal to W of alpha tensor 1. Stone von Neumann theorem says that there is a unitary from our capital K to the L2 R tensor K, such that it is actually looks like W of tensor. I mean, it's just a up to unitary, it is W of alpha tensor 1. Without loss of generality, we assume that it is equal to W of alpha tensor 1. Is okay. So now we want to get a state. So now we want something on L2. I mean, L2 of R is Fock space. Okay. It is just Fock space. Rn. Rn, correct. So I will change it to H. Yeah, it's Rn, correct. You are right. It should be Rn. It's not R. Okay, I call it H. Okay. We fix a N and we are working on N, some generic N. Okay. Okay. It should be finite dimensional. That's all. The Fock space should be finite dimensional. Cn. So, okay. So now we want to get us. So, okay. Now we think about this. So we want to get our K, I mean, we want to get a F as the linear functional, right? Okay. So we want to get something like, I mean, let us do the calculation and what is the natural choice, we can see. So we want to get F of alpha as some trace of W of alpha times rho. That's what we want to get, a rho such that this happens, right? On this here. Instead, we can get that F of alpha let me just directly do it. So consider the following state. Consider the vacuum state. So lambda of 0, lambda of 0. Okay. We take the vacuum state. Okay. Then what is W of alpha tensor 1? What I want to say is trace of W of alpha tensor 1, okay, on this lambda 0. Let's just evaluate this. Okay. This is equal to, which is just trace of this is just the inner product, right? Lambda of 0, U alpha, lambda of 0, right? Which is equal to F of alpha. Let me start from there rather than here. I mean, I want to give the how we get it naturally, but let us do the calculation as it is. Okay. We want to get F of alpha as something, okay, as a state on L2 of Rn. So F of alpha is nothing but, by definition, F of alpha equal to, what is F of alpha? Lambda of alpha with lambda 0, right? Correct? By definition. F of alpha, See, lambda alpha, lambda 0 is defined by the K of alpha. By definition, this is lambda alpha should be there. Okay, you want it. Yeah, it's like this. Sorry. This is the confusion with the inner product, say, which is equal to lambda of alpha. This is the inner product between them, right? Now, this is equal to lambda of 0, U alpha acting on lambda of 0, right? U alpha is just the shift, and in the inner product, all those things vanish because it's 0 there. We define U alpha of lambda beta by something, and the beta is 0. Okay? So we get this. Okay. Now this is nothing but trace. If you remember in the last semester when we discussed the trace class operator for rank 1 operator, is just this evaluation. The trace of this, trace, it is just the trace of U alpha times this. This vector. How do we write it? Yeah, it's okay. Right? This operator. You can bring those brackets to this side and you can do all that. You can work with that, okay? In a trace. That's not an operator. Lambda 0 is a vector. You can consider it as an operator. You can bring it this way or that way. Doesn't matter. You can consider it as an operator on some, from a different.
Which one?
The lambda 0 as a vector can be considered as an operator acting on some dual space or this space or whatever. Okay, so you can play with that. Okay, you can bring that lambda 0 this side, or so you get this. Okay, this is okay. Anyway, check, convince about this. Okay, we have gone through these things in the last semester. Okay, so now it is equal to this. Now here comes the trick. Okay, now this is equal to, so this is actually by definition, this is equal to trace of. This is how our U alpha looks like this. W of tensor 1, lambda 0 times lambda 0. Okay. Now here comes our exercise. This is the assignment. Okay. This is an assignment which was a problem in the end semester exam. Okay. The assignment is the following. If you have two Hilbert space, H1 tensor H2, suppose T is an operator in B of H1 tensor H2, a trace class operator. Okay. Operator. Okay. Then there exists, the uniqueness, all those things we need not go through. There exists, actually it is unique. There exists a T1 in B of H1, again a trace class operator, such that the following is true. Trace of X T1 equal to, this is the trace on the B of H1, is equal to trace of X tensor 1 T. Correct, no?
Partial trace.
This is partial trace. So if you have a big operator on H1 tensor H2, you can trace out over one Hilbert space, H2. Okay. How you get is the following. So this existence is directly this is just a direct theorem, like it's like Rees lemma kind of thing. It's not exactly Rees lemma. See, this X going to this idea is the following. X going to this trace of X tensor 1 T. This is the linear functional on B of H1, right? Is a linear functional on B of H1. That's clear. Okay. Now this linear functional is weak star continuous. That is, if Xn converges to X in trace class, in trace now, okay, then the corresponding thing will converge. Corresponding numbers will converge. You can prove that. That would exactly mean that this is actually given by a T1 like that. That is one way of doing. Okay.
So what's that? Could you repeat the question? T1 and BH1?
One second. I erased something. One second.
Yeah.
Did I erase the such? That's okay. So I will erase this. This is the explanation I gave. Tell me. This is for all. For all X in B of H1.
Yeah.
Tell me. Yeah. What is the question?
X was just an object.
Yeah. I mean, X is any operator. So this gives this X going to whatever that right hand side, X going to right hand side gives a linear functional on B of H1. So any linear, and it is weak star continuous, right? It is weak star continuous. Okay. And that is actually given by weak star continuous means some xn converges to X. I mean, xn converges to, I mean, it is precisely what it means by weak star continuity. Okay. I mean, you understand what is weak star continuous? Weak star continuous is this, the following. If you have a Hilbert space, if Banach space X, such that some Y star equal to X. Okay. Then Xn, something Y star, Y, this is the dual of something. X is the dual of Y. Then we say that Xn converges to X in weak star topology. If phi of, I mean, okay, it's something like this. Now Xn acts on Y as a linear operator, right? So if Xn of phi, Xn of maybe I call it phi n because you want it as a function, no? Y star equal to X. Okay. So X is a linear functional on Y star. Okay. So suppose phi n is contained in X and phi n. So this is the definition of weak star. Okay. Weak star continues phi if and only if phi n of X converges to phi n of Y converges to phi of Y for all Y n. Weak continuity means for any dual, if you apply anything in the dual, it should converge. Xn converges to X in weak topology if phi n of X converges to phi of X. Weak star means you evaluate that and that should converge. Weak star is a topology and a dual space. It should be a dual space to start with. There only you start talking about weak star topology. B of H is a dual space. It's a dual of trace class operator. Okay, so something converges in the okay. So if something converges weak star in the dual space B of H, no, it's because something happened here. It's okay. Just think about it and you can, then you just give the right argument. That's all. Okay. Or you can do the other thing. What you can explicitly give that operator T1. How you do it is, if suppose this is also idea, I will write it and erase. Okay. So if EI is an orthonormal basis for H1, okay, and some Fj is an orthonormal basis for H2, okay, then it is clear that EI tensor Fj, okay, with Ij, orthonormal basis for H1 tensor H2. This works in general, any Hilbert space, finite dimensional, every infinite dimensional also it will work. This is an orthonormal basis for H1 tensor H2. Now, any operator T on H1 tensor H2, okay, that you can write it through this so-called partial isometry. Partial isometry means all those operators, EI tensor Fj, okay, EI prime, I mean the prime should be on the index. EI prime tensor Fj prime. So this is the loose contact, I think. EI prime tensor of J prime. Okay. So you can expand it like this. You will have a constant corresponding to that. So on this, you just sum over Fjj, not Fjj prime. Okay. I mean, the new operator T1, okay, its expansion with the EI, EJ, EI, EI prime. I mean, T1 can be expanded with this partial symmetry, right? Okay. For that will be exactly you sum over just the diagonal part. Sum the coefficient for the T. But you sum over only JJ, not JJ prime. Okay. This is exactly what is called partial trace. You can do it in infinite dimension also. Okay. So that will give the right operator. I mean, you can prove the existence and then explicitly show that this works. Okay. So now we have, and another thing to note is if you have a state on a H1 tensor H2, if you trace it out, if you take the partial trace, that will be a trace on the first Hilbert space. Okay, that is also another one. Okay. So this is the first assignment. Second, if rho is a state. So, and define, okay, let us define this. So you define trace 1 of T is equal to this T1. Okay. T1 is the operator. Or trace 2, I don't know. This is trace 2. Okay. Yeah. We are tracing out the second one. No? So trace 2 of T is equal to T1. Okay. So here I have to trace 2, no? I have to trace this is tensor 1, so I have to trace 2. Now the assignment 2 is if rho is a state on H1 tensor H2, then trace 2 of rho is again a state. I mean, its trace is 1 and it's okay, on H1. That's all. It's easy. You have to show that the trace is 1. And if you can't compute the trace, it will be the trace. I mean, if you compute the if you compute the trace of this operator, this partial trace, that will be the trace of the original T, right? Yeah, that's all. Yeah. So it works. Okay, now continuing this continuation. So now define rho on our H, which is L2R, okay? On L2R by rho is equal to the trace 2 of this. That's all. Lambda 0, lambda 0. Okay. Then rho satisfies. So already we have this trace of W of alpha tensor 1. We have that. I mean, which is equal to that, no? Right? Yeah. Yeah, W of alpha tensor 1. Lambda 0, we have this lambda 0, lambda 0. This is equal to trace of W of alpha rho. I mean, it's true for every X, in particular for W of alpha, right? For all alpha. See, and this is precisely equal to F of alpha. So the theorem is proved. Okay. That's all. Yeah, we just use the vacuum state. If it is irreducible, then the vacuum state itself will work. That's all. Okay. So now let us see some corollary. And the another proposition is this rho to rho hat is a bijection. We have already proved it's onto, I mean, rho to rho hat satisfying those conditions. Rho hat is all those functions. I mean, it's 1, 1, let us say 1. It's a bijection, rho to rho. I mean, it's a bijection onto all functions satisfying those conditions. That's positive definite f of 0 equal to 1. F is continuous and satisfying it's a bijection between them. But we will let's just worry about 1, 1 is 1, 1. Okay. So proof. So we have to worry about, suppose some other f of alpha equal to rho hat alpha. Rho is a state, rho hat is its characteristic function. Then we take suppose f of alpha equal to rho alpha for all alpha in Cn. Then we have to prove that, I mean, f of alpha. Yeah. Then we have to prove that f of alpha, I mean, then we suppose we have another state, no? So then
Rho prime.
Yeah, we have to have rho prime.
Like f of alpha is equal to rho.
Correct.
Alpha.
So we want to prove the one-oneness, no? So f of alpha is equal to rho prime. Shall I use sigma? I will use sigma because the prime and hat confusing. Suppose sigma hat of alpha equal to rho of alpha for two states, for states rho sigma on H. Okay, we have two states on H such that sigma alpha alpha equal to rho of alpha, rho hat of alpha. What does this mean? This means trace of rho W of alpha is equal to trace of sigma W of alpha. Okay. Okay. Of course, this implies one second. I mean, there are few things I forgot to verify. See, I said this satisfies the Stone-Farnham theorem. We have to actually verify that it's strongly continuous, which I forgot.
F is continuous, inner product is continuous.
F is continuous. So we have to verify that the representation is strongly continuous. Alpha going to U alpha is strongly continuous. Which we have to do, which I mean, I forgot to do that. So is there can I make a insert? Good. Here I have to verify that U alpha satisfies CCR, and U alpha is also strongly continuous. I have to verify. Alpha going to U alpha. These are the two conditions. No? It should be strongly continuous representation. That's all. U alpha is strongly continuous. So once I looked at the strong continuity, I remember that. So first thing we should notice is F. What is given is F is continuous. Okay, the function F is just a continuous function. Now we have to verify that alpha n goes to alpha, then U alpha n goes to U alpha. That's what we have to verify. Okay. The first claim is the subclaim. Claim is alpha n goes to alpha, then lambda alpha n goes to lambda alpha in the Hilbert space. Okay, that we have to verify. So why is that true? What is lambda alpha n? Lambda alpha n are vectors in the Hilbert space. Alpha n's are in complex numbers, Cn. Okay, so alpha n goes to alpha in Cn. This happens in Cn. This happens in K, the Hilbert space K. Okay, so we have to prove this. So how do we prove it? So let us compute this inner product, lambda alpha n, this norm, lambda of alpha. We have to prove that this goes to 0. As alpha n goes to alpha, we have to prove that this goes to 0. But there is no way of controlling this. We only know the inner products, right? So we compute the square. See, whenever you want to work with inner product and you want to prove something in norm, you have to take the square. That's what usually we will do in Hilbert space. Okay, that's the usual trick. So if you do that, this will be norm of lambda alpha n square. What is norm of alpha n square? See, we have this condition, no? Our inner product is defined by this. Where is it? Lambda alpha prime is going to be e power minus I something, then f of beta minus alpha or something, no? With that, it will follow that norm of lambda alpha n is f of 0. It's also true that norm of lambda alpha is also true. For any element, lambda of alpha is equal to f of 0. Okay. Right? Which is just the inner product between, square. If you take the square, which is just going to be lambda alpha, inner product lambda alpha. By definition, the imaginary part of the inner product is 0. So it is just going to be f of 0. Okay. By the definition. So this is going to be f of 0 plus another f of 0 minus 2 real part of lambda alpha n, lambda alpha. Okay. Now this is just 2 of f of 0 minus 2 of real part of e power whatever. We have this e power I imaginary part of alpha n alpha. Okay. F of alpha n minus alpha. Okay. Now this alpha and inner product is continuous, alpha n will go to alpha. So then the inner product is 0. Alpha n will go to alpha. Imaginary part of alpha n will also go to alpha n alpha will also go to alpha alpha, whose imaginary part is 0. So it will go to 0. F of alpha n minus alpha will go to f of 0. So which is equal to 2f of 0. So which is equal to 2f of 0 minus 2f of 0 equal to 0. Okay. So we have proved the subclaim. So we have proved that the map alpha going to lambda alpha going to lambda alpha is continuous. Okay. Now we want to prove. Now what is U alpha? Now U alpha equal to, what is U alpha? How is it defined? U alpha acting on lambda alpha. We want to check the following. See, if you have unitaries, you want to check the strong convergence, it is enough to check it on a total set. Okay, if I remember, this was also discussed in the last semester. Did I give it as an assignment? Yeah, assignment or something. Okay. So because of that, it's enough to check to prove alpha going to U alpha is strongly continuous. Enough to prove U alpha lambda beta, U alpha n lambda beta going to U alpha lambda beta if alpha n goes to alpha, right? So that's what we want to. We assume alpha n goes to alpha, then we want to prove U alpha n lambda beta goes to U alpha lambda beta. So let us just check it. So this is equal to e power I imaginary part of alpha n beta f of beta plus alpha n. Of course, f is continuous, inner product is continuous.
Lambda of beta.
Lambda, sorry. Yeah. Sorry. Lambda. Now we have proved that the lambda alpha going to lambda alpha is continuous. The lambda is a continuous function. Okay? So because of that, this will go to U alpha lambda. So hence prove. So we have verified the strong continuity. It's important. The strong continuity we have to verify. Okay? So it's strongly continuous and it satisfies the Weil commutation relation. Then we use the Swan-Van-Neumann theorem to get this. Okay, done. Good. Okay, now we want to verify the injectivity of the quantum characteristic function. If some sigma hat alpha equal to rho hat alpha, then it's true that trace of rho w of alpha equal to trace sigma w of alpha. Okay. Now we know that this trace is strongly continuous. So that was the exercise. If Tn converges, we showed that if Tn, this is true. This implies trace of rho T equal to trace of sigma T for all T in the span of W of alpha. Okay. That is just clear. Trace is linear, so it is clear. Okay. Now we have proved the following. If Tn converges to T strongly, then trace of rho T n converges to, this was the assignment, trace of rho T, right? Because of this implies trace of rho T is equal to trace of sigma T for all T, because strong closure of the span of Weil operator is everything. Okay, for all T in B of H. Okay. Now this implies, this is a linear function, right? This is a linear function. The linear functional coincides on that. Trace, what does this mean? This means that this is a linear functional on, this implies, let's see, phi T of, I will write phi T of rho equal to phi T of sigma. Okay, where T is the linear functional. If we have a bounded operator, see, the dual of trace class operator is this. Okay, how does it act? B1H, this is a trace class operator. B1 star is B of H. Okay. Dual of trace class operator is everything. Okay. So that's what this says. How is the dual acting? If you have a T on B of H, if you have a T on B of H, if you have a bounded operator on D of H, then we can define a phi T on any operator, any T1 to be trace of T1. This is a linear functional and trace class operators. Okay. So this just says that phi T of rho equal to phi T of sigma, where we identify phi T is precisely equal to that. Okay. Which is a linear functional and trace class operator. Okay. So now this is for all T in B of H. I mean, I just wrote phi T. Phi T is defined as the linear functional. Okay. But they are all the linear functional. They give all the linear functional. Now, if you have an element in a Hilbert space, in a Banach space, I mean, this is actually we haven't done in the last course, but you will learn in the later course. Hahn-Banach theorem is a corollary to the Hahn-Banach theorem. If you have some element in a Banach space, if X is a Banach space, so if X is in H, suppose phi of X equal to, I mean, XY. If you have two elements, X and Y in a Banach space, phi of X equal to phi of Y, for all phi in X star, okay, then X equal to Y. This is a corollary to what is called Hahn-Banach theorem. Okay. So you haven't seen Hahn-Banach theorem yet. The proof.
I have, but like, how does this follow?
Okay, good. It's a good question. So let us discuss this. You are attending, you saw in this course, the current course, Ghana 2. You are not attending. So in whose course you put?
Like I read it.
Huh? You read it on your own. Okay, good. Okay, so let us discuss this. Since we are this course want to be complete. Did I?
You use it for these representation.
That reason the C of X.
You can choose T and then show this, right? You can choose, this is true for all T.
Right.
Can you not keep choosing T and then showing that rho equal to
Yeah, the existence of such a T is through Hahn-Banach theorem.
No,
Which T?
now you want to show that rho equal to sigma, right?
Right, correct. Yeah. How will you choose T?
Because the previous step works for all T.
Correct. This is
You choose your T
Oh, wait.
and show that rho equal to sigma.
I
By
think
choosing different T's.
if you have like, if a vector for all functionals, it gives you 0, then it is the 0 vector.
correct. That's what precisely we
Yeah,
are.
so you can extend, you can find a linear function to give the norm of the vector.
Exactly.
Extend.
Which
Yeah.
is Hahn-Banach
Yeah,
theorem.
that's the Hahn.
Yeah, but how will you choose the T in infinite dimension? The point is you will be able to define something on one dimension.
Right, so you wrote it as EJ.
Hmm.
So if rho EJ works for all equal to sigma EJ trace for all choices pi and j, can you not show that rho equal to sigma?
Or like you're picking each element.
Yeah.
You'll have to
No,
pick
you want to choose a T. No, but there is no. But how are you connecting with the earlier one? That was a tensor product.
No, there you said that it can be written as the sum of EJs, right?
Correct.
So
Yeah.
I use the same EJ here for all.
You want to use a EJ for rho, expand rho in that.
No, T.
Yeah. But T is arbitrary T.
Yeah, so you can choose it to be the outer product EJ, right?
Okay. So
So
the
all choices are
correct. Correct. So yeah, correct. That's also right. To take the outer
But
product.
you'll have to do like convergence there, right? Like you'll have to like.
No. For all outer product, if the
Yes.
coefficient for all outer product is same, then they are same.
Because they converge.
See,
Yeah.
that's all. This is what he says is the following.
Yeah.
If you have an orthonormal basis EI, okay, if this is true, I mean, I should write it this way. Yeah, that's right. If you have some, if you have EI, EFJ, some rho FJ equal to EI, sigma FJ, okay, then rho equal to sigma. Okay, you don't need Hahn-Banach theorem. So that's one way of doing. As you say, as he says, this is enough. Okay. This in particular imply that's right. So yeah, this implies trace of rho. You can use EI, EJ. Okay, is equal to trace of sigma EI, EJ. Okay, which is actually this implies EI, which is exactly equal to rho Ej equal to Ei sigma Ej. This is
But one question, so rho and sigma can be I times rho, right?
sigma can be, no, in this condition, no.
No, I mean it's the complex sign.
Yeah, that's what I'm saying. There is no reason why it will be same. If two operators satisfies this condition for all x and y, then they should be same. It cannot be I times A, but it will change. If you put a I, it will change. I will not be observed.
No, it is not consistent with my understanding that if I take a state and change only the complex phase, the measurement outcomes are identical. The statistical measurement outcomes are identical. Maybe I'm wrong.
No, that is because it doesn't change the state in a vector. In a vector state. In a vector state you are talking about.
No, even density operator.
Even density operator, if you
No, maybe you're right. Yeah, I think it's the vector state.
it give the same ray kind of thing. Yeah. The state is same. As an operator, they are same. So if you have a vector state, if you multiply by any any complex number of unit modulus,
Then the
Yeah.
distribution.
it doesn't change. It gives the same state because you get the same. It is like this, no? If you have something x, x, I'm always xx. If you put a unit modulus there, multiply the x with that, it will not change. Yeah, I think it's because of that. This is true. If you have something inner product, this is what is called, it's partial isometries. I mean, these things. This is these are partial isometric, correct? But these are what is called matrix units.
Yeah.
Correct. Matrix unit. I mean, you can talk about it in infinite dimension also. Okay. So this is called what is called matrix units of this. Okay. They are same, then the operators are same. So this implies rho equal to sigma.
Like you still have to make like the convergence argument, right? Like
Which convergent
the-
argument?
This is true because of the thing you told us in last lecture. Last time, like every vector is uniquely represented as summation ei, comma v ei. That's what, that's why this is true, right? So you still have to make the it's fine, yeah.
Okay.
Yeah. All right.
Okay. There is no need, but as I said, you can use the Hahn-Banach theorem also. It will be same for all linear functions, so it's same. Okay, anyway, so this is done. So it uniquely, so the idea is, if you want to talk about the state, it is enough to talk about its characteristic function. Okay, if you know the characteristic function, then you know the state. Okay, because of this bijection. If it satisfies both positive definite condition, f of 0 equal to 1 and all that, then you know the state. So you can work with the characteristic function instead of the actual state. Indeed, it will be very difficult to find what is the probability measure of this P alpha under some state and all that. See, finally, what do you want to do? If you have a state rho, then you want to find the probability distribution on this. Okay, which will be difficult. Okay, how will you find? So you want to see, we want to define a Gaussian state as follows. If you have a state rho, and if this P alpha for all alpha, P alpha is the generator of the W of T alpha. Okay, so if you have a P alpha for all alpha, if it follows the Gaussian distribution, then we call it a Gaussian state. But then it's difficult to find the state of that and find the probability measure on this. It's possible, but we do it through characteristic function. We compute the characteristic function that will be Gaussian, so we know that it's Gaussian. Okay, so that's what we do. Okay, so I'm still having energy somehow. I think yesterday I complicated it by something else. So you want to stop? Maybe I will stop with this. Yeah.
No, you can carry on.
No, but I will do some corollaries. We can do it later. Okay. Yeah. Okay, let's stop.
Thank you.
Okay.